is Dr. Muhammad, and this is a new video under our Seismic Design of Structure course. So today, still we are under the big title of ASCE-7 Seismic Provisions, and today I'm going to talk about two main items. The first one is the effective seismic weight or mass, and the second is going to be the approximate fundamental period that is going to be used for the determination of the seismic base shear. Okay, now let's go directly to the first point, which is the effective seismic weight. Okay, and the word effective here, I'm going to talk about this in a minute, but take care that we are talking about effective. Okay, means that it is not the seismic weight, not all the weight of the building or the structure is going to be included in our calculation, but we are going to have a kind of a portion which is effective during the earthquake or during the seismic excitation. Okay, so this is the we can say the background of using this word, which is effective seismic weight. Now let's go to the section that is dealing with the effective seismic weight in ASCE-7. So actually this is the source from ASCE-7 16, and you can find it under the section 12.7.2 titled with effective seismic weight. So the effective seismic weight, uppercase W here, of a structure shall include the dead load. So this is number one here, dead load as defined in section 3.1 above the base and other loads above the base as listed. We are talking about above the base. Okay, so if we have a structure, okay, we are going to talk about the height or the weight that is above the base. If we say that this is the base of the structure, then we're talking about this weight. This weight is not going to be included with us. Okay, so it is above the weight, above the base. Okay, so and other loads above the base as listed below. So we have like this. The main is dead load. So as we said, the main contributor is the dead load. So dead load should be used always. And some cases, which are 5 cases here, we need to have some guidelines for them. For example, the first case, in areas used for storage, a minimum of 25% of floor live load shall be included. So if you have an area that is used for, take care of this word, storage. So in this case, a minimum, this is another important word, a minimum of 25% of the floor live load shall be included. A minimum means that you can increase this. You can take like 50% if you want. If it's densely stacked, for example. In this case, you can go higher than 25%, and we are talking about live load. But there are some exceptions here. These exceptions are related to the case where the inclusion of storage loads adds no more than 5% to the effective seismic weight at that level. It need not to be included in the effective seismic weight. If we are talking about trivial additional load, which is 5%, this means that it's not really storage area there, and there is no stacked dense stacked storage. Okay, and if the case is the floor live load for the public garage and open parking structures need not to be included. If you are going to talk about public garage and open parking areas, then you are not going to take the live load. What is the reason for this? That first of all, whenever that you have a building, that's unimportant. Whenever you have a structure, for example, and you have different levels here, of course you have like live load going to be existent on each floor, right? The point is live load in general, it is considered to be like loose. Okay, means that it is not physically tied to the floor itself. whenever there is an earthquake is going to strike the building or the structure, the inertia forces are going to be developed based on the fixed physically tied masses or weighted to the structure. So for example, if I have like kind of a car here, for example, small cart that is here and heavily loaded, for example, whenever the structure is going to move back and forth, this car is not going to develop any inertia forces. It is going to roll on the floor itself, so it will not contribute. This is the main idea here, that we use dead load because it is physically, as I'm going to explain, physically tied to the building. Okay? However, live load is not. But whenever that we have areas that is considered to be storage area and the storage is going to have dense, stacked books, for example, or other stuff that is considered to be stacked whenever there is a motion, the inertia force is going to include this mass, or the ground excitation is going to force this mass or weight to develop inertia forces, then we're going to take it into consideration. So this is why the code is very cautious regarding this point. It mentions that the portion of the weight that is physically tied to the building is considered effective. That's the word effective. Okay? So if we go back to the title, if you remember in the previous title, I put that effective seismic weight. So the meaning of effective means that that portion of weight that is physically tied to the building, okay, effective. This is considered to be effective. Live load, loose furniture, like equipment, humans, anything like this, they are not going to develop any inertia forces during the excitation. They are going to roll on the floor, okay, or going to make some friction, and they are not going to develop any inertia forces. Okay, are not considered unless they are used for storage. And if they are going to be used for storage also, not all of the storage. Okay, storage of, like if we are going to talk about public garages, for example, and we have all the cars are packed in the peak hour, and there is a ground excitation or an earthquake strikes the building. All these cars, they are not going, if we are going to talk about this, the cars are not going to develop also an inertia force. They can roll or make some friction. They are going to move. They are considered to be loose. Okay, this is why they put garages and open parking to be from the exceptions. But if I said there is some packed storage area, highly dense, then minimum, it is minimum, means that you can take like 50%, 70%. This is based on the engineering judgment, that if you see that this area is going to be highly dense and packed and stacked with storage materials in a way that is going to develop inertia force and going to be as if it is physically tied to the building, then you can increase it to 70% or maybe more if you want. But the code puts only the minimum. Okay, another source is where provision for partitions is required. In the floor load design, the actual partition weight or minimum weight of 10 pounds per square foot, which is 0.48 kilonewton per meter squared of floor area, whichever is greater. We are having like two options here. If you have partitions, definitely the partitions are going to be like physically tied, if we say, to the floor. So we have two options here: to take the real weight or the actual partition weight, or you put 0.48 kilonewton per meter squared. Okay, you're going to look and take the higher or the larger among them. Number 3, it is the total operating weight of permanent equipment. Okay, if you have a permanent equipment, definitely the weight permanent means that it is physically tied also. Then all the weight total, take care of the word total. Where the flat roof of the snow, flat roof snow load PF exceeds 30 pounds per square foot or 1.4 kilonewton per meter squared, 20% of the uniform design snow load, regardless of the actual roof slope, will be taken. This is important. 20%. I'm going to talk about this in the next slide. Okay. Weight of landscaping and other materials at roof gardens and similar areas, they are going to develop. Okay, they are going to develop some inertial forces if they are like going to be tied to the building. Okay, the important hints here are that in the effective seismic weight, all permanently attached equipment, as we said, like air conditioners, for example, elevator equipment, and mechanical systems, okay, they are going to be used. Movable partitions, a minimum of 10 pounds per square foot is required, and 20% of significant roof snow load. These are already mentioned as I have read them. Certain types of live loads, such as storage loads, may develop inertial forces, particularly where they are, that's the reason here, or this is the main reason for them, densely packed. If this reason or cause is existent, then we are going to allow this live loads to contribute in our effective seismic weight. The full snow load need not to be considered, because if you read before, I said before, we were talking about 20% of the snow load. So why the full snow load need not to be considered? Because maximum snow load and maximum earthquake load are unlikely to occur simultaneously, and loose snow does not move with roof. Okay, that's right also. Again, for two reasons. The first one, that maximum earthquake and maximum snow, they are not unlikely to occur simultaneously. And also whenever that we have some snow, okay, on the roof, for example, it is loose by default. Only 20%. If we have something like this part is not going to work with us. Maybe this part, which is as if it is fixed or physically tied to the roof, for example, would work. So this justifies the 20% that the code is stipulating. Okay, now let's go to the next important part for our lecture for today, which is the approximate fundamental period. Again, from the title, I want you to take notice about this word, which is approximate. We're not talking about accurate. Here, we are talking about approximate, fundamental period. So, and it's not calculated as well, okay? There is not calculated. Calculated means that if we have a building and we are going to analyze the building using any software package, for example, and then we can get the natural frequency and the natural period and whatever that we want, the dynamic characteristics of the building. But actually here, the code is providing a tool for us based on approximate methods and empirical formulas. So it is not accurate and it is not calculated based on the analysis, which is another alternative that we are going to talk about it. Okay, so take care of this word. We're talking about approximate, fundamental period, okay, period of the structure. Really, I have explained about the fundamental period and the fundamental frequency before in the previous videos, so please revisit these videos for understanding these items. Now I'm going to talk about different points here under the fundamental period. I'm going to touch upon the period, why we use this T in equivalent lateral force method, why this is the basis for ASCE. I'm going to talk about the computed period, T computed, and the approximate T, what is the difference between the two, when to use and when not to use. And I'm going to talk about period computed using computer programs, some hints about it, and computing TA, or the approximate period for masonry and concrete shear wall structures. We're going to talk about this, and periods of vibration for three-dimensional systems. And lastly, I'm going to give an example from the Seismic Design Manual based on IBC 2015. Okay, so this would be the main contents of this video. Okay, now let's go to the first point, which is period T and the rationale behind it, behind using this for the equivalent lateral force method in ASCE-7. You're going to find it in section 12.8.2.1. Okay, so let's have a look on it. Here, this is the section. Okay, 12.8.2, and under it, this section. Here we're talking about period determination in general, and then we're talking about the approximate fundamental period. And as you can see, we have like three different equations. We have, this is equation 1, equation 2, and equation 3. So let's go back. So we have like three basic formulas are provided for us. We have three different approximate t's are provided for us. The first one, it is the general. Okay, all of them, remember, these formulas are highly empirical and are to be used for seismic analysis of building structure. We are not talking about non-building here. It is only for building structures. Okay, so this equation, it applies to all buildings. This one, okay, CT times HN to the power X. And this TA, it applies to certain moment frames. This is for certain moment frames. Okay, and this one, it applies for shear wall structures, whether masonry or concrete. Okay, so we have all buildings, moment frames, shear walls, or shear wall structures. Okay, these are categories of these three different approximate methods for determining the period of the structure. So this is actually the code here. Okay, this is the code stipulating this. I'm only going to like highlight the important things here regarding this. There are some like limitation on T, as we are going to see. The fundamental period of the structure T in the direction under consideration shall be established using structure properties and fundamental and deformational characteristics of the resisting element in properly substantiated analysis. Okay, that's the meaning, means that rigorous way of modeling. Okay, so the fundamental, this is key also here. Okay, keyword is accurate analysis. The fundamental period T shall not exceed the product of the coefficient of upper limit. Then we're going to talk about some upper limit here, as you're going to see, which we call it CU from a table on TE. So we are going to put like upper limit CU times TA. This is considered to be the upper limit for us. As an alternative to performing an analysis to determine the fundamental period T, it is permitted to use the approximate building period TA calculated in accordance with this section. So here the code is putting it as an alternative. Okay, it is an alternative to performing an analysis to determine the fundamental period. It is permitted, so it's allowed for us. It is permitted to use the approximate building period TA, which is going to be calculated from the three different equations here, or based on the structure itself. Okay, so the first one, this is the general one, as we said. So this is going to be used in general. The second equation, which is 0.1n, it is an alternative. It is permitted to determine this approximate from this following equation for structures not exceeding 12 stories above the base, as defined in section 11.2. Okay, and the seismic force resisting system is concrete or steel moment resisting frame. So this is for concrete and steel moment resisting frame. Here, this one, as we said, it should be for shear wall structure not exceeding 120 feet or 36.6 meters in height. Okay, so this is limited with 12-story. This is limited with 120 feet. Okay, so we have some height limitation on this. Okay, and this CW here, it is going to be used from this equation. We are going to look to this whenever that we apply an example for this CW or for the shear wall structures. Okay. Now let's go to the, here I mentioned that there is C upper, which is the upper kind of upper limit on the T. This upper limit is going to be obtained from this table. Okay, so we're going to find here coefficient C upper, and this is in table 12.8-1. We call it coefficient for upper limit on calculated period. Okay, In the lift column, we are putting SD1, and there is some ranges for this. I'm going to talk about this ranges shortly. And the coefficient ultimate, it ranges between 1.4 to 1.7. 1.4 to 1.7 means that almost we are putting a cap like 50%. We're putting 50% increase as upper limit on the T approximate that we are going to use. Okay, 50% as an average I'm talking about here, because we have 1.4, 1.7 as limits. And this is the CT and X that is being used in the main equation. We have here T, CT, and H to the power X. How we can obtain them? We can obtain them from here. This is structure type. Here this is CT and this is X, and it is for different types of structures. We have like 4 different categories. The first one is moment frames, okay, with some description. Steel eccentric braced frame, and we have steel buckling restrained braced frame, BRBs, and all other structure systems, which is most commonly we use for our structure, 0.02 and 0.75 for X. Okay, now let's go to the purpose of T itself and understand more about it. Actually, the main purpose of T here in the ASCE, it is a tool for us to obtain the design base shear. Okay, so we're not going to use it for anything else. Okay, except in some exceptions we are going to use some other TS later. I'm going to talk about it, but the main purpose of T here, not to know what is the fundamental period of the structure or something like this. It's not considered to be a dynamic characteristic. Of course it has this meaning, but we are not seeking or searching for a specific or particular dynamic characteristic of the structure. We are seeking for a kind of an estimation of the period of the structure that is going to make our structures to be safe and to some extent conservative. Okay, so the fundamental period of the structure T is used to determine the design base shear as well as the exponent K that establish the distribution of the shear along the height of the structure. So we can say that T is used for 2 main purposes. First one is base shear on the bottom of the structure. Okay, so this is the base shear mainly. And the other one is how this base shear is going to be distributed along the height. Okay, so this distribution, there is a factor called K, we're going to talk about it later, that needs to be determined as well. So this T is providing for this K. So it is the total base shear and the distribution of the base shear. These are the main 2 purposes of our T. This equation, which is the main equation, which is 8-7, it is based on statistical analysis of the measured response of building in California. So this is an important issue, because if we're talking about other places, so this empirical formula may not work. If you look here, this figure actually illustrates the data for various structures for steel moment resisting frames. So we have the building height here, and we have the fundamental period here. If you look here, the dotted line is the mean. Okay, all these dots and crosses, they are like the relation between the building height and the fundamental period. So we found that they are making this scatter, this kind of different scattered, or this pattern of points. So we put their mean, which is the dotted line, and we put the mean minus 1 standard deviation, which is the black line here. This black line is considered to be our equation. We are having the lower bound. So we are having a lower bound. Why it is a lower bound, not the mean, or if we say that if there is a like upper bound, yes, we should take T lesser. Why? Because in the response spectrum, if you remember, we said that especially in the velocity sensitive region, the increase of t is going to decrease what? Exactly, is going to decrease the spectral acceleration and consequently decreasing the base shear. However, in our design we want to be conservative, so it's not good to have upper bound of the t, but it's better to have the lower bound, so that t is going to be conservatively, if the actual t of the building here, conservatively we are going to assume it here, and then we are going to, or here for example, then you are going to find that our base shear and spectral acceleration is higher, so that we are going to put more, the design would requiring more cross sections. Okay, so remember from here that t is based on statistical analysis. So t is based on statistical analysis, and it is for California, so it is only for California. If we're talking about other places, so it might not work for us. Okay, so this is why you have to keep this limitation in your mind. You have to keep this limitation in your mind, statistical and California only. Okay. Why we need this conservative estimate of base shear? Okay, since the empirical expression is based on the lower bound of data, it produces lower bound, as we said, for the period of building of given height. That's right, and we have explained this. Okay, lower bound. This lower bound period used in equations. These are the equations here, equation 3 and 4, as you can see, because t here and t here, t in the denominator. This means that the larger the t is, the lower the CSS, the coefficient of the base shear. So it means that for t less than TL, okay, and for t larger than TL, both of them we are having t in the denominator. This means that it is inversely related to the coefficient of seismic coefficient. So it's better for us to use conservative approach or conservative estimate of the base shear. So we are going to decrease t, so we're going to make it less in order to increase the CS, because at the end our CS is going to be multiplied by the weight. So having larger value of CS is going to make us have conservative value of the base shear, or conservative magnitude of base shear. Okay, so that's the rationale behind the conservative estimate of the base shear. The fundamental period determined from a rational analysis, okay, may be used in design unless it exceeds the approximate period times the coefficient of provided in table 12.8-1. Means what? You will have t calculated, okay, which is from the software package, which is coming from analysis. It is allowed for you to use, okay, as long as it is what? Less than, or unless it exceeds the approximate period times the coefficient. It should be always less than the CU times t approximate. If your t calculated is less than the upper cap of the approximate period, then no problem, you can use it. But if your t calculated is going to be higher than this value, this is the upper value that you should use in that case. Okay? Okay, so this period limits prevents this period limit, which is C ultimate, or the cap here, limit prevents the use of unusually low equivalent lateral force base shear for design of buildings or computational models that are overly flexible. What is the meaning of this? Actually, it is a very nice word, and instead of using the word that is the computational models may not be accurate, or there is some errors in your model. In the models or computational or analytical models, usually we have some errors, which is going to make our t calculated, going to make it larger than the right or the exact value or the true value of the building. So the code is putting this limit, which is using the coefficient C ultimate here for this purpose. So if I ask you, for example, what is the main role of C ultimate in designing or seismic design? The answer is, in order to prevent or avoid any inaccurate computational models, then we use this upper limit. Why? Because in our models, computational models, maybe we are going to have flexible structure, overly flexible structure. Why? What is the reason it is flexible? Why not stiffer, for example? Because mostly whenever that we use accurate computational models, the panel zone and the connection between columns and beams, we are going to connect them using some springs or some modeling techniques that would allow this frame or this subassembly to work more flexibly or to show more flexible behavior than the actual one. So this is why the code is putting this limit. He's saying to you, hey, do not go and follow your computational models, because maybe it's not true and it's not actually that what you are going to see in the in reality. So they put this limit. Okay, so remember, C ultimate works only for preventing us from following some inaccurate computational and analytical models. So the period upper limit factor effects, we have like two effects for the factor C ultimate from the table 12.8-1. Actually, you are going to find that, first of all, it has different values based on what? Different levels of SD1, right? So if SD1 is 0.4 or 0.3 or 0.1, 0.1, so whenever that SD is decreasing, okay, then our C ultimate, as you can see, it is going to be, the limit here is going to be like going larger, because this is larger than, if SD1 is larger than 0.4 or larger than 0.3 or less than 0.1. If it's larger than 0.4, means that our SD1, it is going to be very high, right? So this means that the seismicity here is high, and then the coefficient corresponding is going to be less compared to the cases where that SD1 is smaller than 0.1, where that this coefficient is higher. So first of all, this table is establishing for two things. First, the conservation of lower bound empirical formulas of TA is removed. Because if you remember that we have like lower bound, right? Do you remember from the curve, there are some points here, and we are talking about the lower bound, right? So first of all, this table is removing this. We are now increasing. Instead of saying that T is going to be controlled by this, we are going to say that no, it will be here, for example. Why? Because we multiply it by almost 40% higher, at least, right? So this is number one. And number two, second, the period is increased in regions of lower seismicity. The period is increased in regions of lower seismicity, as buildings in such areas generally are more flexible and hence have longer periods than buildings in region of higher seismicity. Commonly, the buildings in lower seismicity zones, they are, like, as we said, they are more flexible. They are more flexible, okay? Because there is no care regarding the connections and so on. So we're going to find that in low seismic areas, the structures tend to be more flexible. More flexible means that they are having longer period. So this is why whenever that we go in lower, as I said, if SD1 is going lower, this means that we are increasing the upper limit factor. So we're increasing T going up. Okay. Why? What is the reason? Because of this. This is the rationale here, that in lower seismicity areas or regions, the buildings tends to be more flexible. So we put like something to reflect this fact. Okay. Now let's go to the next Actually here only what we want to highlight from this part, that this is talking about that we have already used T for base shear. But what I want to highlight here is that generally conservative, okay, we say that it's generally conservative, this T in general, because periods computed on the basis of rational structure analysis are almost always greater than those computed from the empirical formulas. So this needs to be highlighted here. Whenever that you are making a computational model or empirical model, the periods computed on the basis of your rational structure analysis are almost always greater than those computed from the empirical formulas. So do not worry. Whenever the T approximate is 0.5 and your real structure is giving you 0.7, then it's okay. Okay, this should be considered as okay. Okay. So this is why we put the like the upper limit. We want to limit this this model or T calculated, because maybe there is something wrong. Another point is what we are doing here. It is for equivalent lateral force method. This is for strength design. Means that we are going to use this T for base shear calculation. But if we're going to talk about period, drift calculations, there is the standard, actually section 12.8.6.2 of the standard allows the computed period to be used in the development of an alternative set of equivalent lateral forces that are used only for drift calculation. Why? What is the reason for this? Actually, T coming from the calculation of the analytical model, or the T calculated from the analytical model, it is, as we said always, it is larger than T approximate. And whenever this is T calculated is larger, this means that the structure is more flexible. More flexible means what? More drift. So this means more to be more conservative. So this is why we use it for drift calculation. Okay, for drift calculation. Okay, so we have like two approaches. One approach for strength and equivalent lateral force for the base shear and the distribution of the force on the members, and there is another way for the drift, the base shear, that is going to be used for the calculation of the drift. It should be T calculated, should be or allowed here to be used. Why? Because it is more conservative. I'm going to talk about the drift calculation later in next videos, so do not worry about it. Okay, now let's have an example, a short example to understand what we are talking about. If let us assume that we have T approximate that we have obtained already from our standard is 0.525, and T computed from our analytical model is it is 0.921 seconds. We're talking about seconds here. So this is computed and this is approximate. So if we look here, T computed higher and larger than the approximate one. Then we should go to the table, our table 12.8-1, and then look to C ultimate, the upper limit that we should use based on SD1. Let's assume that we have SD1, it is an assumption for us, it is 0.25 G. So we are here, 0.25 G. So we are talking about this here, something in between. So this means that our C ultimate by interpolation is going to be between 1.4 and 1.5. Okay, this is going to be in between. Okay, so this means that if we have this is the interpolation, so the value here is over 2. So C ultimate in this case is going to be, yes, the average of those, which is 1.45. And T is going to be, which is the upper limit now, is going to be applied 1.45 times our T approximate, which is 0.76. Now compare this 0.76 with the T computed. It is what? It is less. So the upper limit works well for us. We're going to limit the T that is going to be used for base shear by this value, not this value. The period of 0.761 must be used to determine the set of equivalent lateral forces from which strength. Take care, we're talking about strengths, not talking about drift or serviceability. Okay, of the structure will be evaluated, even though the rational period T computed was somewhat longer at 0.9. Okay, because we are talking, or we are standing in the conservative side always. So if we could find a conservative side, then we are going to put ourselves in T. In order to obtain the base shear, T is better to be less, not to be large, okay, or larger than the approximate one. Okay. 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 So this is the case here for for us. Okay. Now let's go to the second point, which is computed period T, which is T computed, and approximate T. There is like different situations for our case. Okay. Sometimes when you use the computed, okay, let's assume, for example, that the computed period T computed was 0.615. Here it was, the T computed was 0.9, okay, and T approximate 0.525. Let's assume that this is not 0.9 here, it is 0.6, as he said here. It is 0.615. This means that it is less than 0.716, which is the upper limit, right? Actually, the code is silent about this issue. He didn't mention anything about this. So although ASCE-7 is silent on this possibility, it is recommended that the lower period be used in the calculation. Lower period. So we have, this is the upper limit, and this is the T computed. Here it is recommended. It is recommended to use T computed. Why? What is the reason? Because as I said, we need to be conservative. So this is less, then it will give you higher base shear, then you use it. This is even that the code allows, but we are going to be in the conservative side. Okay. In the unlikely event that the computed period turns out to be less than T approximate, for example, if T computed is 0.4, okay, the period T is going to be 0.525 in this case, because this is very, very conservative kind of, if we have like T calculated, we found it 0.4, however that T approximate is 0.5, well, this is, yes, we can take this 0.4, but again, this is too conservative. The code allows you to take this TA. Take care, this is by default, it is conservative. Okay, because there is no requirement that T computed shall be determined in this case. Okay. If the computed period is significantly different from C ultimate or C upper TA, for example, it's too small, or too, if we are talking about too computed, for example, it is less than 0.5, okay, C ultimate TA, so if it's less than, so this is T calculated, is less than 0.5 CUT approximate, or larger T computed is larger than 2 times, for example, okay, C ultimate TA. In this case, there is something wrong in your mathematical model or computer model. You have to revisit it again. Okay, so take care of this. So it's very good practice for all of us to use the T approximate in general, but in some certain cases we need to use the T computed. The next slide, I'm going to show to you a table that summarizes this. So here, this is the summary of the period values to be used in calculations. So this is the situation: T computed less than TA, or T computed larger than TA but smaller than the upper limit, or T computed is larger than the upper limit. So if we are going, we have two columns here. The period that should be used for, take care of this word, strength calculation here, and the period that should be used for drift calculation. Which one that we should use? Here, in the first case, T approximate should be used. Actually, in both cases, it should be used, because if T computed is less, it is not recommended at all to use less than T approximate. It is not recommended to use T computed here. because there's something wrong with you. Maybe, or because as we said, T approximate is conservative. No need to add more conservatism, okay, by using T computed. So in both cases, we're going to use TA. If T computed in between, okay, between approximate and the upper limit, then you can use it for both, actually, for strength and drift. If T computed is larger than this one, which is the upper limit, then use the upper limit for strength, but use T computed for drift. This is logic. This is conservative for both sides. Okay? Okay, this is the summary of when to use T and when T computed and T approximate. Okay, now let's go to the next, which is hints regarding period computed using computer program. This is only like few hints. I want you to take care of it whenever that you are making your model, and remember why the ASCE is very strict regarding using the T computed from the models. The computed period depends directly on the assumptions made in modeling. That's very important. So the mass and stiffness of the various components of the structure and the boundary condition. Mass, stiffness, and boundary condition. So it depends on this. So if I use the same or create the same model that you are creating, but I used some different ways for the boundary condition or the stiffness, then definitely our T calculated is going to be different. So the main source for the change of T is coming from the stiffness, which is related to the flexibility. And we found that deformation in the panel zones of the beam column joints of steel moment frames are a significant source of flexibility in these frames. So take care of the panel zones, especially for steel people who are working with steel and so on. So the panel zones in the beam column joints are considered to be the source of flexibility. Your definition and modeling, if it's different than mine, then we're going to have different computed T. Full rigid end zones, as allowed by many computer programs, should never be used. Take care of this. Most of us actually are falling into this trap, which is we are using the rigid connection, which is not right. It should never be used because they always result in overestimation of the lateral stiffness. You are going to have your structure to be very stiff if you are putting rigid connections between beam and columns. Okay, you are going to find your T to be excessively small, and then you are going to find that your base shear is very high. This is why we call it overestimation. And partially rigid end zones are appropriate, so we recommend for you to use this, which is the partially rigid end zones, okay, in the modeling of joints, especially for RC buildings. Okay, so do not use total rigid and do not use over flexible, but like semi-rigid or partially rigid end zones. Another thing that is important, especially for reinforced concrete, that the cracks, okay, cracking in all structure elements should be taken into consideration. ASCE, for example, because it will affect the stiffness too much. ASCE 41, for example, recommends that 50% of the gross section is used for beams, and 70% of the gross section used of the moment of inertia be used for columns in compression. Can you imagine? It is 50% is not working with you for beams, and here only 70% is working, and the 30 are not working for you. So take care of these different hints regarding the period computed using your computer model. You need to be careful when you are modeling. Okay, now let's go to the next point, which is the shear wall structure. Actually, the determination of the T approximate for masonry and concrete shear walls, it is given by this equation, which is equation 9. Okay, and this is TA, and we have CW here, which is going to be calculated from this equation. HI and DI, it is already related to the plan. of the structure itself. So we have like AB here, which is area of the base of the structure. AI, which is here, it is the area of the web of wall. I, if we are talking about some wall, because in the area we are going to have different walls, so there is a summation here, as you can see, a summation sign. DI, it's the plan length of the wall, and X is the number of falls in the direction under consideration. This is from I equal to 1 to X. So we are going to find this CW and put it here, and you have the height, and you can use. But my recommendation for this is, I put it here, that it's better for you to model it using finite element analysis program, really, especially for shear walls. Okay. So a better approach for determining the period of vibration for shear wall systems is to model the system accurately in finite element analysis program. This is done quite conveniently with modern software. Why I'm saying this? Because really you're going to find that there are some overestimation, as we said, not necessarily to be taken into consideration, and they are putting here as an alternate method, okay, for computing TA. So it is an alternate method for using TA for masonry or concrete. Okay, so it is based on you and based on your judgment, but I strongly recommend that to use finite element method here. Okay, it's better. Okay, and last thing is the period of vibration for three-dimensional systems. Here I'm talking about something which is related to the modeling itself in the three-dimensional modeling technique. You are going to find that you need to be careful, because whenever that you are modeling 3D structures, you are going to find three different types of mode shapes, which is two perpendicular, and another one maybe it is torsional, for example. Then you need to take care of this. Sometimes whenever you look to the fundamental periods, which is T1, T2, and T3 of the structure, you're going to find that T1 is not giving you what you are expecting. And whenever that you work with the mode shape and check it, you're going to find maybe some beam, it is highly flexible, so it gives you the maximum T. Or you have a cantilever that is not fixed well, or it is not working on your system, that is giving you T1. Okay, so this means that, or a kind of error in the connectivity. So this means what? This means that you need to check your model over and over again. Okay, so here I said that the first mode, or any of the first several modes, can also represent a vibration of flexible portion of a system. Yes, if the portion, there is some part that is flexible, it would give you the first mode. So this is not right. You are talking about the global stiffness of the system and the global period of the structure, such as long cantilevers, as I said, long span beams, or even an error in connectivity. Thus, for using the periods in analysis, the engineer should plot and animate, that is then important, plot and animate the mode shapes to make sure that the proper periods are being used. Reviewing the mass participation of each mode is also a good indicator of structure behavior. So you have two things here, like animating and plotting your mode shape. This is option 1 to check. Option 2 is checking the participation mass ratios. The highest mode should have the highest mass participation ratio. Okay, the last thing is an example for what we have explained before. So I'm going to talk about the example from Seismic Design Manual 2010, okay, following ASCE-7, okay, 10. Okay, let's look here. This is only an introduction for the problem that we know that we are using this as an alternative to analyzing a structure to determine its fundamental period. The approximate fundamental period may be calculated by this section. So what we want to know here is what CT and H of the structure. Okay, and X we are going to obtain it from the tables. Okay, so the coefficient CT and the exponent X are dependent on the type of the structure system used. Based on this, in this example, we have five different buildings, and we need to check every one of them. Okay, now let's go with the first one. It is, we have steel special moment frame, concrete special moment frame, steel eccentrically braced frame, masonry shear wall building, and concrete shear wall building tilt up construction. So let's go with the first one here. So let's assume this is our structure. This is our structure. We have the grade here, and we have like 96 feet superstructure, and we have 22 feet like substructure or basement, which is consisting of shear walls, as you can see here. One of the important things here is the height, which height that we should use. So height of the structure above its base is 96 feet. We chose to take this. You're going to ask me, what about this part? Okay, this is a great deal of like discussion. You can find it. I'm going to refer to it again. But whenever that we have basement and shear walls, we are going to consider that the structure is as if it is fixed underneath. So it is as if that it is like a cantilever. Okay, it is cantilever, and this part is stabbed into the foundation. So the height that we are going to use is this one. Okay. Actually, it is not in every case. Here we have shear walls for basement, but it needs to consult and also to have a kind of consultancy with the geotechnical engineer to know the type of the soil and whether they can provide a lateral stiffness to your foundation or not. So that's an important issue. Okay. And I'm going to mention about this in the comment. That is, you are going to see it in commentary C11.2 in ASCE-7. Okay? But anyway, let's go now. So our height of the structure is 96 feet. The addition 22 feet, the additional 22 foot depth of the basement is not considered in determining H for period calculation. We're going to talk about it in the below note as I'm going to explain. CT equals to 0.028, X equal to 0.8. From where we got this values? So let's go here. I think that the table, from the table itself, it is, yes, not here. So sorry for this. It is the table that, yes, from here. So we're talking about, it was steel moment resisting frame, so we are going to talk about 0.028 and 0.8 for CT and X respectively. So we are going to go back here. Okay. So here we have 0.028 and 0.8. Then TA is going to be CT H to the power X. H is 96, CT already, and the X is known. It is 1 second. Values of CT and X are tabulated as we said. This means that this is an approximate one and conservative T as well for our moment steel special moment frames. Okay. Let's go to the note. Actually here in the 1999 SIG Blue Book, which is very important reference actually for us also, and you can have a look on it. It's very detailed and a very nice book for giving some insights regarding the different seismic approaches. Base is defined as the level at which earthquake motions are considered to be imparted, or the level at which the structure as a dynamic vibrator is supported. So this is the definition in the SIG. For this particular structure, the rigidity of the basement shear walls and surrounding soil compared to the superstructure moment frame is judged to be sufficient. Look to this word, judged. By whom? It is by the engineers. Okay, this is why I said to you that you need to consult the geotechnical engineer. Ask him about the lateral stiffness of the soil surrounding your basement, whether it can work with you to be really sufficient support for the superstructure or not. So judged to be sufficient to consider the base at grade level. So we're going to consider it as at the grade level here. This is the level from which our height should be measured. The engineer of record is ultimately responsible for establishing the appropriate level of the base for use in the seismic analysis. And if you need to know more, you can refer to commentary C11.2 in ASCE-7-10. Okay, so actually here only it's a kind of like I'd like to highlight the meaning of the spirit of this small note. I think that you need to remember two things. If we're going to consider this grade here, above the grade, this medium, it is the soil, and this medium is the superstructure. We consider that it's highly dense here, and then it is considered to be like the start of the real superstructure from above the grade. But if we have the structure is going to go underneath the grading level, and there is a basement, for example, so you need to look to the basement wall and the surrounding soil as well. Are they going to work for us or not? So if they are going to work for us as support, then our height should be from above the grade, and this would be considered as if it is fixed under the soil, and it is considered to be like foundation. This is the grade for us. However, if the basement walls, as you can see here, it is thin, it is not thick like this one, it is thin, okay, and the soil provide some lateral stiffness, it is the same as here. So we are not sure actually what will happen. Should we take it from here, the height, or should we take it from here? Based on this, we take it as average in between. Why? What is the reason for this? Because we are not sure. We are not sure what will happen. The wall of the basement is not that thick, and the lateral soil, maybe it is okay for us to consider there is some lateral stiffness from it, but at the end, we cannot judge it. So based on this, we consider it as halfway through in between. So H is going to be like halfway through. If I clear this up, so here, remember well, if the basement is having thick walls and rigid enough with the surrounding soil, if you know it from the geotechnical report and the geotechnical engineer, then you can consider the height coming from here, and all of this is like the base for the structure. However, if the basement wall is thin and they are flexible, not rigid, and the soil is providing some lateral stiffness, then you can take the height starting from halfway through here, from here, okay, not from above the grade. Okay. This is only a small comment regarding this note. Let's go to the next. So now let's go to this, which is concrete special moment frame. So we have this shape, which is, as you can see, it's irregular. So we have like 33 feet and 22 feet, and we have a setback here. Why we have chosen this is because it is a little bit confusing for us, which height that we should use, this one or this one, okay, especially in setbacks. And actually this is the importance of this example. The height of the tallest part of the building is 33 feet. This is used to determine the period. We are going to use this one. Roof penthouses are generally not considered in determining HN. Roof penthouses, if we have something like this, and we have like small something penthouse above here, this will not be provided in our H. Our H will be like this. But our case is not penthouse, it is setback, it is different. Okay? So penthouses are not included in our H, in our HN. However, if the setback represents more than 30%, yes, but heights of setbacks are included. So our setback, there is a setback here, then the height is going to be included. This height is going to be included in our total height. However, if the setback represents more than 30% change in lateral force system dimension, there is a vertical geometric irregularity based on table 12.3-2, and dynamic analysis is required for this type of irregularity in accordance with table 12.6.1. Okay, so anyway, what I want you to remember, penthouses heights are not considered, setbacks are considered, the height is considered, unless that they are like representing more than 30% change in lateral stiffness. Okay, in this case we will not use this way. Actually, we need to make dynamic analysis. So in our case, H is going to be 33, CT 0.016, and X is 0.9. This is from the table that we have seen. I just want to highlight, yes, from the table, it is this one, okay, 0.016 and 0.9 for concrete moment resisting frames. So we are on the right page here, 0.016 and 0.9. Okay, so this is the second example. Let's go to the third one, which is steel eccentrically braced frame, EBF structure. So from the code, it is from the table, it is steel eccentrically braced frame. Then CT is 0.03 and X is 0.75, 0.03, 0.75, and T is going to be 0.51. No problem with this. Okay, and then the last one is masonry shear wall. So masonry shear wall, it is under the all other structure systems. So we're going to have 0.02 and 0.75. Then we're going to have 0.02 and 0.75 here. Then it would give us 0.25. If you look to the roof here, okay, the roof here seems to be like flexible roof. Masonry shear wall building, okay. Sorry. Yes, this is masonry shear wall building. I'm sorry, this is the roof. We're talking about H here. So in this case, H is going to be 29. Look here, it is H here, it is 29 feet. 29 feet. Okay, so you are not talking about the parapet, for example. You are talking about the roof itself, where it is. Okay, and the previous one, yes, this is the eccentric brace. We have it at the roof also level. Okay, now let's go to the concrete shear wall building, tilt up construction, tilt up. So we have something like this here. So the roof here is going to be taken, this is the height, which is 20 feet. Okay. Consider a tilt up building 100 feet by 20 feet in plan that has a panelized wood frame roof. So the roof is panelized wood frame roof, and the typical wall elevation shown below here. This panelized wood frame, it is a little bit flexible. Okay, so we can say that this type of structure, first of all, if you want to look to the table, you're going to find it under the all other structure system. So 0.02 and 0.75. 0.02 and 0.75, and then you substitute in the equation, you will get it 0.19. But there is a problem here. This type of structure system has relatively rigid walls and flexible roof diaphragm. So the equation that we used, it is not used for this kind of structures actually. It is, we have very rigid walls and the roof is very flexible. So are they going to work together or not? We do not know. The code formula for period does not take into consideration the fact that the real period of building is highly dependent on the roof diaphragm construction. That's right, because the diaphragm of the roof is going to connect the elements together. Now we are talking about this roof to be flexible. So how it is going to be reflected in our period? Thus, the approximate period computed above may not provide a good estimate of the real fundamental period of this type of building. It is acceptable, however, for use in the determining base shear. So this means that take care. The main benefit of this example is take care. Not everything given in the code is going to be applicable in your in your building. So you need to be careful. Okay, maybe the flexibility of the roof would not allow you to use the period. Even that at the end they said that it is acceptable to use this T, but it is strongly recommended here to what? Use the T computed if you are sure from your analytical modeling. Okay, I think this is the end of this this video, and I hope to see you in the next video regarding the base shear. Thank you very much, and see you in the next video.